Thank you, everybody. Thank you so much for having me here. This is amazing. It's been a very great day, catching up with a bunch of familiar faces and meeting all new people here. Thank you. This is great. Okay, I'm Chris Mendillo. I work at UMass Lowell. I'm a research professor there. I've been doing this project basically for the last 15 years since I was started as a grad student at BU, making iteration after iteration, trying to get it to finally work. I work on a mission called Picture C. This is a balloon-borne NASA high-altitude mission to do direct imaging of exoplanetary systems around nearby stars. This is Picture C at its float altitude of 130,000 feet above New Mexico. We were just out in New Mexico from July through September, getting ready and then launching this mission. This entire observatory was built by 4 or 5 people at UMass Lowell in our lab. It's a great testament to their work over the last 6 years, and so I'm very excited to tell you about it today. At 130,000 feet, you can see the sky is dark. It's pretty amazing that you can do astronomy, even visible astronomy during the day. So this is Picture C. It stands for something. I wish I could remember it. I think this is the correct version this time. It's Planetary Imaging Concept Testbed using a Recoverable Experiment - Coronagraph. That's our mission. It has, every time we do it, it's a different combination, but it's always the same name. So the idea is we want to directly image exoplanetary systems being dust and debris and eventually exoplanets themselves around nearby stars using a modest size 60 centimeter telescope and a device to block out the starlight called a vector vortex coronagraph. A vector vortex coronagraph is just one of many different architectures for blocking the light of a star. We inherited the word coronagraph from solar coronagraphs, even though it's a completely different technology. What we build is the center body of this assembly here. This is our gondola, the bigger thing. The inner bit is our telescope. We're held on a thing called WASP, which stands for Wallops Arc-Second Pointer. It's a pointing 2-axis gimbal pointing mount that points the telescope to within, or does sub-arc-second stability pointing on the sky. And NASA built that at Wallops Flight Facility. And then below here is our gondola. You can see the cables. Those go up to a big spreader bar that then hooks onto a thing that rotates the whole telescope in azimuth. And then you have a huge flight train of cables and then eventually a parachute and a balloon above you. This weighs about 6,000 pounds. Our telescope is 1,500 pounds. It's about 12 feet long. Oh, I should say, we flew once in 2019. That was our first engineering flight. We've tried again to fly in 2020 and 2021, and those didn't happen for obvious reasons for COVID, and then I'll show you what happened in 2021, and then we finally flew again in 2020. This is the team. The majority of the work is done by the people where it says UMass Lowell. This is all of us color-coded by our helmets out in New Mexico. Supriya Chakrabarty is the mission PI. There I am, and at the time these were grad students, Kuravi and Glenn. They've both got their PhDs on the program. Okay, so this is the idea. This is the big picture, for lack of a better word. In the next 20 years, we want to take a picture of an exoplanetary system like our own solar system, and be able to resolve and detect planets like Earth, Venus, and Jupiter in a single image. And then we would do something very simple. Use a spectroscope, put a spectroscopic slit over a planet and measure its spectrum. And this is a simulated Earth analog planet. And so you'll see there's a lot of features as you get into the infrared. We work mostly in the visible. But the most difficult part of this graph is the y-axis, where you'll see the planet to star flux ratio, which is something we call the contrast ratio, how bright the planet is relative to the star, times 10 to the 9th. So an Earth-like planet is 1 billion to 10 billion times dimmer than the star that it orbits. And being able to image that and detect that next to an incredibly bright star is very, very challenging. So that's the problem we're trying to make steps in solving over the next 20 years till we get a flagship mission to do this. The problem we have is simple. It's diffraction. If you have a circular telescope, you don't get an infinitely small image of a star. The star image, because of diffraction from the finite aperture of the telescope, forms an airy pattern, and you have these wings that kind of just go out forever. And if you take that and plot it in 2 dimensions, the black line is the star, so it's normalized to 1, and its point spread function dies off, but in logarithmic units, it pretty much hits a plateau and just goes off forever. And if you're trying to image a planet that's a billion times dimmer, even if you put it off axis to the star, it's still 10 million to 100 million times dimmer than the background signal that you're trying to see. So this is the challenge. Need a way to block the star without blocking the planet. That's where the idea of a coronagraph comes in. And there's 2 different kinds of coronagraph right now that we're developing. There's an external coronagraph, which is a huge disk that, this is completely the wrong scale. To get them both in the same image, they had to do this. But these things would be flying 50 kilometers apart from each other. A huge thing called a star shade, which has these petals that are made to control diffraction. And you could fly these 2 things, a telescope and a star shield, fly the star shield in front of a star, block out the star, and see a planet sitting next to it. The benefit of doing it this way is you don't need a special telescope. So any space telescope will do. All the engineering goes into building this incredibly large star shade that you have to do formation flying with, which is difficult, certainly. The other way to do it is what's called an internal coronagraph. So take the coronagraph that blocks the light of the star and put it inside your telescope. And that's what Picture C does, and it's a simpler idea, but it requires a more complicated instrument. This is why we can't do exoplanet imaging with Hubble, because it doesn't have a coronagraph, and neither does any other space telescope. And the idea here is you take the light from your telescope and you focus it onto what is essentially a black dot on a, we're basically putting our thumb in front of the star, right? So a black dot on a piece of glass, it's a very complex black dot, and it will do something to the light to get the starlight to go away so that when you get down to a final image plane, you could see your planet next to the star. I'll go into more detail about how the coronagraph that we work with, how that works. So a little bit of background, what's being done right now from the ground in space. A lot's being done from the ground with big telescopes like Keck. So this is an image of the most famous exoplanet system. This is HR 8799. There are 4 planets orbiting this star, and you can take an image like this with Keck. This is taken in the infrared. We are actually seeing the emitted light from these planets. So these are younger versions of Jupiter, and they're pretty warm. So they're emitting a lot of infrared light out at 3 point in L band. And you can see the actual emission. So in that case, the contrast ratio is much more favorable. I'll show a plot in a few slides that kind of puts that into perspective. But these might only be 10,000 times dimmer than the star, not a billion times dimmer than the star. Here they are again. This is them taking 7 years of data from Keck. You can actually see them orbiting. And you can use this orbital motion to enhance the data processing to really make the planets pop out. This is the Beta Pic system where it has this really bright debris disk of dust. Excuse me. And then if you zoom in on the interior of the system, you'll see the planet. This is 51 Eri B, another animation where you can see the planet actually moving. And you can this is taken with the Gemini Planet Imager, which is GPI, which is on the Gemini telescope. And they actually can get infrared spectra of the planet. This is a really cool image from GPI of a dust ring, a debris disk ring. They have a polarization instrument in their instrument, so they can measure dust polarization. So it's kind of hard to get the perspective right, but this is the back edge of a dust ring, scattering light, single scattering light to you from the back edge of the system. And dust scattering, especially single scattering, is highly polarized. And so you can use the polarization filters to get a better idea of the morphology and the dust grain composition of these systems. From space, this is a catalog of all the disks seen by Hubble. Hubble doesn't have a proper exoplanet coronagraph on it, but it has a very simple coronagraph on the NICMOS instrument where you can do some amount of starlight suppression and you can measure all these really cool disks. What Hubble has to its benefit is just a ton of observing time and really, really good imaging quality. And you take a huge data set and they've developed incredible imaging processing techniques to take all of that and come up with all these different decompositions of the PSF and back out these incredible images of dust rings. So for the future, for the near future, this is where we're headed. This is what used to be called WFIRST, is now the Nancy Grace Roman Space Telescope. It's going to launch in the mid-2020s, and this has, for the first time in a satellite mission, a dedicated exoplanet high-contrast coronagraph. This is what it looks like. It's great to see they're actually building this thing. It's an incredibly complex optical instrument. All the optics are up here. All the electronics are down here. They do that for they want to keep the two things as thermally isolated as possible. And this is at JPL, where they're actually putting this together right now. So they've got all the mirrors aligned. They're starting to integrate the electronics. I'll talk more about deformable mirrors in a minute. If you know anything about adaptive optics for telescope systems, we use the same all the same tools, but we use them in a slightly different way. We're not trying to keep up with the atmosphere turbulence. We're trying to correct at incredibly high precision imperfections in the optical system. So these are the flight DM's deformable mirrors for CGI, which is chronographic instrument. Okay, so this is the plot I was talking about. Direct imaging people love to show plots of apparent separation versus contrast. All right, so all the planets I've been talking about so far are up here in the top right corner. These are all bright infrared planets that are at 10 to the minus 5 or 10 to the minus 4. And they can be seen from Earth. But planets like our solar system are down in this bottom left corner. And this is the really challenging corner. So what we're trying to do is move from this top right corner down to the bottom left, where we get closer and closer to the star and at much higher contrast ratios. So something like Earth, the number to remember is 10 to the minus 10. You need to block out the starlight to a part in 10 billion. To be able to see the planet. And to do that requires an incredible amount of precision in your adaptive optics system. So those missions I talked about at the beginning, the flagship mission for the 2040s and then Roman CGI are going to occupy this sort of area. So we're making big steps. These are all ground-based systems. These lines correspond to their detection limits. So we're moving towards this bottom left-hand corner. Picture C, our instrument, is making the next order of magnitude improvement over what's possible from the ground. That's what we're trying to do. And this is Picture C's mission in a single slide. A system like one of our nearest neighbors, Epsilon Eridani, which is a K2V star. It's a solar-type star. It's got a known asteroid belt. We know that from infrared excess measurements. We know it has a debris disk from submillimeter measurements. And we know from radial velocity measurements that it has an exoplanet, a giant Jupiter-like exoplanet, orbiting in a Jupiter-like orbit. And we've built our telescope and our system for it to fit perfectly into the field of view. So this is our field of view. This is the solar system to scale. And we're trying to take a picture where we see this ring of dust. No one's ever done that before. And to do that, we think we need about 10 to the minus 7 raw starlight suppression and use a 60 centimeter telescope. That's our goal. So this is Picture C. We've been designing and building this thing since 2015. I'll just give you a brief overview of how it works. There's a telescope out front. There's electronics in the back and avionics for the pointing system and counterweights. This whole thing is balanced on this center hub, which is where it connects to that WASP pointing system. We use an off-axis telescope, which you may not have seen before. If you imagine a telescope as the primary mirror is a big parabola, instead of having a big mirror with a hole in the middle, we take a section off-axis of the primary mirror and just build the telescope with that section. And so what that lets us do is not have a hole in the center of the beam. It lets us not have these support structures for the secondary mirror. It gives you a perfectly circular disk of light coming from the telescope. And that's really important for doing these high contrast observations because all those defects in the pupil of the telescope diffract light all over the place, and are very, very challenging to work with. So we've gone with the simplest possible telescope design, which is this off-axis parabola system. We have a secondary mirror that's mounted on a hexapod. This talk is going to be very heavy on engineering and optics, and there's a little bit of science at the end. But I hope by the end of this, all of you will be able to, in a pinch, build your own space telescope to fly in a balloon, all right? So I'm going to tell you how to do it. So the hexapod, this telescope is made out of aluminum. So the whole thing, when it gets up to altitude, it gets cold. It gets down to minus 40 degrees C. The whole telescope shrinks 3 millimeters. The secondary mirror needs to be aligned to micron precision. So we have a hexapod that moves it around. Then we have this chronographic instrument sitting up off-axis to the telescope. So that's this cool off-axis design lets you kind of stack the telescope this way instead of having to put all the optics behind the primary mirror like you have with Hubble. So then all the electronics and everything are on the back. It has a lot of different systems. It has adaptive optics systems. It has this coronagraph system. We have to do really high-speed stabilization. We're blocking out the light of the star, so the image of the star has to stay centered on that coronagraph really, really, really precisely to like milli-arc second on the sky stability. So we need to do really high-speed control systems for that. We need to do really low-speed, high-precision control systems for blocking out the starlight. And there's all sorts of thermal and mechanical drifts and all things going on. And we're in this very dynamic environment of a balloon, which is not like space at all. There's gravity. You're swinging under the balloon. There's all these, there's very little residual atmosphere, but a lot of other dynamics to deal with that you wouldn't have to deal with in space. So I'll give you just a brief or a more in-depth view of how the adaptive optics system and how the coronagraph system works on picture C. So first, this is just a schematic of a generalized adaptive optics system. You have a telescope, the light comes out of the telescope, it bounces off of a deformable mirror. So this is a typical deformable mirror. This is the one that we fly on picture C. It's a centimeter across, it's a little circular mirror, but distributed over that circle are 1,000 micro actuators. So the surface of the mirror can deform itself to sub-nanometer, picometer precision and accuracy. And you can use that to correct the distorted image from the telescope. So the light bounces off the DM, as we call it, and goes to a wavefront sensor, and you can pick off a bit of the light, and the wavefront sensor measures the shape of the wavefront of light coming from the telescope. And you can feed that back to the DM and use it to create a perfectly in focus image from your telescope. And that's how it's used on the ground. For ground-based AO systems, they run the DM really fast, like 3,000 cycles per second, and they're trying to keep up with the atmospheric turbulence. And I'll show you how it works on our system. The next step is the vector vortex coronagraph. So this is a really cool device that I don't pretend to really understand how it works at a very deep level, but this is what it looks like down here. So if you looked at it with your eye, if you just picked it up, it's a clear piece of glass. It's a completely it's a phase device. It's not. There are many different groups of coronagraphs. There are some that work with amplitude and some that work with phase. This is completely phased, so it's completely clear, and it's made with liquid crystals. If you look at it through crossed polarizers, you can see this strange spiral pattern built into it. And what it is the way we say it is it's an azimuthally rotating half-wave plate. So as you go around in the azimuthal angle, like this, the direction of the fast axis of the half-wave plate is changing with angle. Okay, so complicated, but if you apply that phase change at an image plane, so you take your light from your telescope, it's collimated, comes down to an image plane, you send it through that vortex. It's other people call them optical vortexes, okay? And then you go back to a pupil plane, you're taking the Fourier transform from the image plane to go to the pupil plane. And when you do that with this type of device, all of the light that goes through the center of that vortex gets diffracted out to very large angles. So when you go to a downstream plane that's in a pupil plane, all of the starlight gets diffracted out into this ring. And you can put a physical stop there, like a piece of paper with a hole in it, right, and block out all that light. And then the planet light, which does not go through the center of this, goes off axis to this, that makes it through, and it makes it through to the detector. So that's the basics of how it works. This is the spiral phase pattern that gets baked into this using this liquid crystal deposition technology. These are built by only a few companies in the world. It's being pioneered mostly at JPL, the design of these things. And this is the idea that if you go through the center, the light gets diffracted out. It's really incredible. It's just this clear thing. You stick it in the beam and the light just goes, phew. It's just kind of magic, but it works. It's great. So all the light goes out to the sides. If you go off axis to the center, which is where the planet would be over here, that light goes straight through. It doesn't get diffracted. Okay, so I'll take you through the steps of how we get from just an image of a star to a coronagraphic image where we can actually see a planet. So if you had this simple version of a coronagraph where you just have light coming from your telescope, you go off a deformable mirror. This is just a 1D version of it. The deformable mirror surface is going to be represented here. This is where the vortex coronagraph would go. It's not in there right now. And then this is the downstream pupil, which we call the Leo stop. All right, so this is what the light looks like. So in this case, there's no coronagraph. You just have a beam of light. It's just a circle. At the detector, it's just an image of the star. We normalize it into logarithmic units, so it peaks at 1. And then this is the contrast ratio. So starting off around the star, we would want to work in this annulus here. That's where we would look for planets. The leakage is at 5 times 10 to the minus 4. Still way too bright to see a planet. Okay, so we put our coronagraph in, and with a perfect system, all the light gets diffracted out. None of the light goes to the image plane. All of a sudden, we've got perfect contrast. Okay, not how it works in reality, because we have errors on all of our optics. So we have to model all of this stuff. We have to give the vendors who make all the mirrors really precise power spectral envelopes on how the ripples of the mirror have to meet our spec. So they have to stay below this blue line. This is the size of the spatial frequency of the errors versus the amplitude. So this is a typical mirror, the surface map of a typical mirror in our system that meets this spec. So all the optics have to be really, really high quality and polished to this very specific specification. So you do that, you put those optics into this optical simulation, and you see all the light comes back. So even though you still have this vortex pattern, you're still getting a lot of leakage to the center, and you're getting all of these speckles back in your detector plane. Okay, so then you're going to use the DM to fix that. And if you do it the classical way, like you have on the ground, and you just correct the phase of the light, because you just have a mirror, and it's just in a pupil plane, so it's hard to imagine it correcting anything more than phase, because it's a mirror just correcting optical path length. So you do that, you put this correction, this is a 2D, an image of the deformation of the mirror. So this is in nanometers. These are all the little actuators poking up and down on the mirror. You do that, and it cleans up the image a bit, but you're still stuck at 10 to the minus 5, and you can't do anything. So at that point, you're kind of stuck. You need a new way forward to be able to get to much higher contrast. And so what people have come up with to fix this problem is something called electric field conjugation. So this is the next step, and we do this, there are a couple of different ways to do this. We do this completely in simulation. So we build this entire response matrix for our deformable mirrors in simulation and then apply them to the instrument, and it has to be calibrated well enough to work. So this image is a representation of the deformable mirror, okay? So that circle is all the different, in each little square is all the different actuators of the deformable mirror. That's what the light is from the telescope is bouncing off of. Each actuator, that square, is showing that actuator's influence on the image plane. So this is the image. This is where the star would be. This is where all the planets would be. This is the influence of that actuator on the real component of the electric field. So we take all those numbers. We also do the imaginary component of the electric field. Take all of that and form a huge response matrix, which is here. This is what we call the DM influence matrix, or the Jacobian matrix. We have to then invert that so that we could measure a field and calculate the correct pattern to put on the DM to make the field go away. And that's what we do. So we use an SVD, a singular value decomposition technique to do that, apply a bunch of regularization to damp out all the high frequency modes that we don't want. And when you do that, you're able to then make corrections beyond what you could classically do with phase alone. And this is what we do. So we take measurements from our detector plane and feed them back into our DM, and we make extremely precise, less than a nanometer, certainly, adjustments to this DM, and it carves out what we call a dark hole. A single DM can make half the image dark. If you have 2 DMs, you can make the full image dark. But this is what we're left with. So this would be our search region to be able to look for planets. And we can get down to, and this picture C is designed to be able to get down to 10 to the minus 8, just in raw contrast, just with the coronagraph. Yeah?
Is there an easy way to understand why it's just half?
Yeah. The way I always say it, which is not entirely correct, is that, you can think about it as like you're putting the light from here over here. You're kind of shoveling the light over to the other side of the image. That's how it's been explained to me, but it's not exactly correct. We're making both phase and amplitude corrections to the This isn't going to answer your question. I don't think I'm going to get a satisfactory answer to your question, but I can explain a little bit more. We're making phase and amplitude corrections. So it's really interesting that as pure phase corrections propagate through a system, they go through this transformation called the Talbot transformation, where they oscillate between phase and amplitude. So it's like a diffractive process. So you can use that to your advantage, to use a device that's purely phase correcting to actually influence the downstream amplitude. So you're correcting for things like, the mirror reflectivity is not perfect, or it varies. Just like the surface varies, the reflectivity also varies. And so you can use the DM to correct for that too. And it's got to do with the degeneracy between phase and amplitude, that you can only do it on half the image. But yeah, that's as best I'm going to be able to do right now. Yep. Okay, so how to get to 10 to the minus 8 and beyond. There's a lot of things you have to control for. All polarization effects, broadband performance of your coronagraph, surface scatter. You have to be able to build this. We have to do polarization filtering. We have to do all these things. There are all these things. The dynamic things, the things that change in time, are a lot harder to do on a balloon. We have this high-speed stabilization we have to do. We have thermal deformation, gravitational deformation of the telescope. So these are the things that we're always trying to work on. And it's harder to do these on a balloon than it is in space. So these are the challenges that we face that are particular to being in a balloon environment. Okay, so now I'm just going to take you on a slideshow of putting this thing together. So this is picture C. I explained already all the different parts. Here's our telescope. So the telescope mirror is a 2-foot, 24-inch slab of ultra-low expansion glass. It weighs 250 pounds. We're using mass to our advantage here because we have a pretty high mass budget. So it's very thermally stable, and it's mounted on this primary mirror mount that we designed in-house. Our mechanical engineer. Our engineer, whose name is Jason Martell, I'll show you a picture of him in a second, designed this, and it glues, the entire mount glues onto the back of the mirror. It's kind of terrifying the first time you pick this thing up, because it's 27 little 1-inch pucks that glue on with a rubber adhesive epoxy onto the back of the mirror, and then the whole weight of the mirror is just held by that. And we do that to minimize the amount of deformation that the mount places on the surface of the mirror. And then our secondary mirror mounts onto this hexapod that can move around in 6 degrees of freedom. Here we are gluing the mount onto the bottom of the mirror. Here's Jason in our lab at UMass Lowell in our clean room, putting the whole stack together and then picking it up for the first time. We mount it onto our telescope. Here's the telescope truss assembly. This is all aluminum, welded just down the road at an aluminum fabrication lab that we found. We actually got the whole thing painted at an auto body shop that's in Lowell, just down the road from us. We gave them this like special epoxy white paint and said, "Can you use this?" And they were sure. Sprayed the whole thing. Pretty cool. Okay, so these are electronics in the back that control all the deformable mirrors. We have a flight computer. Here they are in real life. Ton of wiring that we had to do. We do all this stuff in-house, so all the flight computer has thousands and thousands of wires coming out of it. Power supply, DM controllers, hexapod controllers, temperature monitors. All of that goes up to the Coronagraph. This is the optical design of the Coronagraph. I'll give you just a brief tour. So light comes in from the telescope. We have two wavefront sensors that are sort of classical wavefront sensors that we call low-order wavefront sensors. So these are ones to measure like telescope aberrations, like focus and coma and astigmatism. There's one up here that has a really large dynamic range. It's called a Shack-Hartman wavefront sensor. I'll show you a picture of that in a second. And then there's one down here that's called a LEO, reflective LEO stop. So that LEO stop, that image I was showing you in the little simulation of how the Coronagraph works, all the light from the star ends up in that plane. So instead of just throwing it away, we use it to measure the stability of the telescope and be able to feed back from that into one of our deformable mirrors, which is sitting up here. So we have a high-speed deformable mirror and a low-speed deformable mirror. This is the one that does the dark hole. This is the one that does the stabilization. This runs at up to 1 kilohertz. This one runs really, really slow, like an update every minute. Okay? We go through all these optics. We come down. The vortex Coronagraph is here. We bounce over here. We go into, this is a cool camera design we came up with that's a bunch of stacked dichroic filters. And it gives us 5 bands of imaging on the sky across our visible bandpass. We're centered at 600 nanometers, so like in the red. Okay, these are the 3 wavefront sensing techniques that we use. So the Shack-Hartman is one of the oldest types of wavefront sensor. They're very robust, very easy to use. It's a micro lens array. So it's 150 micron, tiny little lenses printed into a grid that you put right in front of a detector. So if you put a beam of light on them, you get hundreds of little images that are subapertures of the beam. And so you can look at, as each little spot wanders around on the detector, that gives you a measurement of the local tilt of the wavefront in that subaperture. And so you can measure the centroid of the spot and back out what the shape of the wavefront is. So that's one way. So that's what we use to focus our telescope with that hexapod. Then that reflective LEO stop is a cool design that's been developed in the last 5 or 10 years, where you take that light and you re-image it down to a detector that's slightly out of focus, and that lets you break degeneracy of, gives you a polarity to your correction. So if you were right in focus, you couldn't tell the difference between plus and minus focus, but if you come out of focus, then you can break the degeneracy of that. So different aberrations give you a different characteristic pattern on that detector of the intensity. And so you can then take all this information and again, put it into a big matrix and invert it, and you can then measure the pattern on the detector and come up with a solution to correct with the DM. And then finally, in the actual image plane, so this is where we're going to do the dark hole to dig this really high contrast image. We want to measure the electric field at the image, which is really hard to do. You can't split the light out and then measure it somewhere else, because then there will be all these different errors that you're introducing into the system. So we measure the electric field in the actual science camera. And we do that by placing different probe patterns, different patterns on the DM, which is in a pupil plane, that correspond to, there are these cool, these interesting sync functions that when you take the Fourier transform of them to get back to an image plane, they correspond to discrete steps in phase. And if you have 4 equally spaced images with differing phase, like pi over 2 phase steps between them, you can take those 4 images and use them to reconstruct the electric field. So we do that. So we have to take 4 probe images to get 1 measurement of the electric field, and then we feed that back into that huge matrix and come up with a solution for the DM. So those are the 3 primary wavefront sensors for picture C. Okay. Here is the a 3D rendering of the Coronagraph. And here's the real thing. It's fun to flip back and forth. Everything lines up pretty well. We did a good job. That was the first flight Coronagraph. This was sort of a test. We didn't have the deformable mirror installed in the beam path yet. We were just testing out all of the other systems. For the second flight, this is the second flight Coronagraph where we integrated everything. We got rid of that 5-band camera, so this is just a single broadband image. And this is what we just flew. These are those deformable mirrors. They're all in these. This one's on this really nice integrated controller. And then this is a different one. So these are from 2 different companies that we've been working with over the years. Here's the full Coronagraph in its box. It's built on a carbon fiber optical bench to minimize deformation from the thermal environment. And we put this whole thing in our vacuum tank and do thermal environment testing on it. We cool it down to minus 40 degrees C, make sure everything still works, put it in a vacuum, make sure it all still works. We assembled the whole thing and put it in a big FedEx truck and shipped it down to Wallops Flight Facility in Virginia. This is for our first flight, meeting up with the WASP team. This is Jim Lanzi. He runs the WASP team at NASA. Here we are integrating with the pointing system. There's our gondola for the first time, mated with the pointing system. Then we take that whole thing and ship it out to New Mexico to launch. This is our facility in Fort Sumner, New Mexico. It needs a new paint job, unfortunately. It's even worse now. I mentioned it to them, but they said it's hard to get money to paint the building. I don't know. Anyway, here we are. September 28th, 2019, this was our first flight. This is rolling out at 5 a.m. This big launch crane drives us out. We're on a municipal airport, so there's tarmac and runways out here, and they lay out the whole balloon and inflate it, and we launch from there. And this crane drives us out to the launch site and then launches us. So in the first flight, we had a lot of different things we wanted to demonstrate, and everything worked really well. We demonstrated this low-order wavefront sensor system. That's that reflective LEO stop camera that is showing us stabilizing all these different, we call them the Zernike modes, if you've heard of those. That's like focus, astigmatism, coma. They're orthogonal functions on a 2D aperture. So we use those to describe this. So this is us stabilizing those Zernike modes. All the low-order wavefront sensor worked. The telescope worked. We were able to acquire a number of different targets throughout the flight. I mean, the basic thing is that we built this thing in our lab. We tested it as well as we could, but then we flew it up to 130,000 feet, and all the electronics worked. Everything worked as expected. So last year, we had a COVID year. We didn't get to fly. Last year, we delivered the instrument. We went down to Wallops. We did a bunch of testing. We had some interesting vibrations during the first flight that we tried to fix structurally. So we did a bunch of testing in their clean room there. And then we shipped out to Fort Sumner. And we sat in Fort Sumner for 6 weeks. And it was windy every day. And every day we got up and got a new weather report, and it was windy again. And we tried to launch 5 times over 3 weeks and didn't launch. Had to go home. So we packed up, went back home. This is as close as we got. You can see the parachute laid out there on the ground, but no balloon. Once they take the balloon out of the box, then you're pretty much going. So we never got to that point. We went back to UMass Lowell for 8 months. And then we came back a year later. So I just want to show you quickly what we were able to do in those 8 months. We did a lot of testing with our Coronagraph wavefront control system. We demonstrated this alternate technique to doing the dark hole, which is a more robust and simple technique called speckle nulling, which is you just use the DM to hunt around and find solutions that remove speckles in your image. So this is our flight GSE interface. Is one screen that we're looking at that shows like the Shack-Hartman wavefront sensor, the reflective LEO stop wavefront sensor, and then the commands from the different DMs. And this is the science image down here. And this is the D. That's the D that we're trying to make really dark. And so we run this, and you'll see up on the screen up here, we're just fitting sign patterns. Sign patterns in the pupil plane correspond to dots in an image plane. If you just take the Fourier transform of a sign pattern, you get a a specific spatial frequency that's a dot in your image plane. So we're just hunting around, picking the brightest speckle, and finding the sine wave on the DM that cancels it out. So we're able to test this. So this gives us a more robust way of doing wavefront control on the sky if the electric field conjugation is not working. And we were able to test this on the sky during our last flight too. As you can see that working. And if you flip back and forth, you can see how the speckles and this D are going away, right? And that's the DM command that we get. We also tested the actual electric field dark hole conjugation algorithm better than we had ever tested it before. You don't need to worry so much about these plots, but here, this plot up here in the top left corner is the most important one. So this is in a full broadband. This is a 20% bandpass, so from 540 nanometers to 660 nanometers, we're blocking out this light pretty well, down to almost 4 times 10 to the minus 7. We're hoping to get to 1 times 10 to the minus 7. There's a lot of reasons why we didn't get to 1 times 10 to the minus 7. We are trying to understand them and get there, and we'll try to get there for the next flight. But that was the record we were able to do in the lab. Okay, and then this is an animation showing how our telescope alignment system works. So here is a camera that we stuck in that just looks at what the pupil of the light coming from the telescope looks like. And this is a really out-of-focus telescope. And then we have our Shack-Hartman low-water wavefront sensor. So you see how this is just a low-res version of this. These are where the beam is filled out. And then this is the position of our hexapod that's going to correct it. So we start this thing running, and the system automatically senses the aberrations and drives the hexapod. These are all the 6 axes of the hexapod, drives them to correct the telescope. So every time we look at a star in flight, the telescope is distorted by quite a bit from the thermal deformations, and so we have to run this system. So we're sitting there watching it converge, and eventually it fills out the beam. The beam gets nice and circular, and we have a nice in-focus telescope. We also developed what's called a STOP model, a structural thermal optical performance model. I have a grad student, Thad Potter, who's been working on this. We have about 100 temperature sensors that we flew on the telescope to give us an idea of how the whole thing was deforming during flight. And so he's developed a big optical thermal mechanical model that takes all of that data and tries to predict how the system is deforming and how it behaves in the environment. This is a sort of a work in progress. The lines are the data, the circles are his predictions of what the data should be, and he's seeing that things are cooling off in his model a little faster than they should be, so he's working on that. So this is a big part of his dissertation, is the thermal modeling. So, 8 months later, we're back in Fort Sumner. September 28th, again, 3 years to the day from our first flight, and there should be sound. We got one beautiful morning.
Okay, give me the balloon.
Oh, not loud enough. But he said, that's Larry. He's driving this vehicle out here. And he says, okay, give me the balloon. And they release the balloon. So you can see, this is as much as they inflated the balloon. They cinch it here. This thing will fall off at some point. This is all still balloon down here. The balloon, when it's fully inflated, is 400 feet across. So if you imagine a football stadium or a soccer stadium, it would fit comfortably in the bowl of a soccer stadium. It is an enormous balloon. 40 million cubic feet of helium to fill it up. It's not that much on the ground. It expands as we go up. And then this is the view from the payload. So we're on that launch vehicle, and they let the balloon go, and he's going to drive it and, look out the window and, get underneath it so that the payload doesn't swing too much when they let it go. So you can see the shadow of our payload here. That's the launch vehicle, and then you can faintly see the balloon out here. And he does this thing where he pushes us kind of, and then releases it and drives away, and we float away. And so you can see on the ground, this is where they lay out the balloon. I'm standing right there. My grad students are over there on that. You see that thing fall down? That's what they call a collar. That's what's cinching the top of the balloon to keep all the helium in the top bubble so it doesn't disperse and fly out. And then we'll sweep out over the bustling metropolis of Fort Sumner, New Mexico, where there are more cows than people, as they say. There's one place to stay, the Super 8 Hotel, which is right down there. That's your only spot. And you can see the runway and the airfield where we launch over. And then it's a 3-hour trip to 40 kilometers above the Earth. And we had a great flight. We flew for 18 hours. We drifted. This is our ground track. We were at the end at 2 a.m. We were headed right towards White Sands missile range. So the guy came downstairs, the flight commander came down and said, okay, we probably have to cut you down. We don't want you to go over the missile range. So at 2 a.m., they push the button. The payload terminates and breaks away from the balloon. It rips a huge hole in the side of the balloon. So the balloon actually just free falls, and it's 4,000 pounds of plastic and steel just drops out of the sky and doesn't kill anyone, which is kind of amazing. And we come down on a parachute, and we have a nice soft landing on a ranch like this. This is how they find us. If we're lucky, many people do not get lucky, and they hit a tree or they land in water. It can be a rough landing, but we were very lucky to get 2 really soft landings. And so I'll just show you just a few highlights of the mission. I talked about that really high-speed stabilization of the pointing. That's something that we really care a lot about. To be able to do the high-contrast imaging, you have to really stabilize the telescope pointing. So the telescope is bouncing around at sort of arc-second levels. We have to then stabilize that to milli-arc-second levels. And we had a wide variety of different environments as we were flying due to different changing conditions in the balloon. So that's what we're really trying to understand now. But this is an example of, on the bottom here are pitch and yaw plotted in time. So the blue line is what the telescope is doing, and the black line is our optical stabilization of what the telescope is doing. And then this is a power spectrum. I would be remiss if I didn't have a power spectrum in my talk, because I remember being here and every single talk had a power spectrum, probably of the CMB background in it, and I had no idea what they were. But I'm very glad to be showing my own power spectrum here today. So this is just temporal frequency versus amplitude of pitch. So you can see we're stabilizing really well at lower frequencies, and we have a pretty clean signal up at higher frequencies. Higher frequencies are really bad because we can't control them. So anyway, if you look up here, this is 1.4 milliarc seconds and 0.9 milliarc seconds. I think this is the best anything has ever pointed at anything in the history of telescopes. Hubble does 5 milliarc second pointing. This is from a balloon. We're doing record-breaking pointing stability. We saw a lot of different environments. We saw things where we had a lot of jitter, and there were high-frequency jitters happening. We saw really big amplitude kind of meandering around on the sky, or oscillations on the sky. You can see this big peak. Out here are low frequencies. Low frequencies we don't care about too much. We can stabilize them. We saw really big amplitude drifts. We think this huge drift, this is like 12 arc seconds, is coming from the telescope itself thermally drifting. So these are all the things that we're working on. And then finally, we did demonstrate a dark hole on the sky. This is the deformable mirror on the right and the image plane on the left. You can see us digging this hole in the image plane, the speckles going away on the right side of the image. This is where we ended up. We didn't do quite as well as we do in the lab. We did about an order of magnitude worse because of all that instability I showed you in the previous slides. So we get down to 4 times 10 to the minus 6 suppression. Not bad, not the best, but this has never been done before. So this is the first dark hole on the sky from an instrument not bolted to the surface of the Earth. So I think it's a pretty good step forward towards the ultimate goal of imaging a planet. So, science? Did we do any science? We don't know yet. We're working on the data. We're trying to understand, because of those instabilities that we were seeing, we were never able to hold the dark hole for very long, so we weren't able to get into the final mode of our image acquisition where we would take really, really long exposures. So we had to take a lot of short exposures. We have hundreds of short exposures. We're going to put them all together and see what we find, but I think it's probably unlikely we'll get an image of a dust ring, but it's still possible. Anyway, we'll get a lot of practice analyzing this data for the next flight, and we have a ton of engineering data to improve things for the next flight. So I know I'm pretty much out of time. Just a vision for the future. We have 2 missions on the docket that we're working towards, Picture D and Picture J. This is there are 2 different sort of price tags. Picture D was selected just recently. I am going to be the PI of Picture D. It's a improvement and reflight of Picture C. We're going to add a number of different upgrades. I can talk about those more after the talk if you want. And we're scheduled to have, it's 5 more years, 2 more flights. And so we're really looking forward to continuing our work with Picture C and with WASP, and we've got a bunch of new partners. And then Picture J is a bigger version of this, where we're going to fly a 1-meter telescope from an ultra-long duration balloon platform, where we could fly from New Zealand and fly up to 100 days and circle the Earth. So that's where we're headed. We want to get to here so that we can do actual exoplanet science, image a Jupiter like Epsilon Eridani b, a Jupiter like exoplanet. And the idea here is we think we can do a really good contribution, a scientific contribution with a very simple instrument, because we've tuned all the optics to work in the blue. So the Roman Space Telescope is going to work out in the red and the near infrared, and they're going to measure all of these molecular features of the spectrum of a planet. And that's going to be great. And we're going to do complementary observations in the blue, where the spectrum is not dominated by molecules. It's just dominated by scattering in the atmosphere. And so with just 3 measurements, 3 bands, we can measure the slope of the spectrum and determine, is it dominated by water clouds? Is it dominated by hazes and aerosols? Or is it dominated by colder, this is a Jupiter spectrum, colder ammonia clouds, and things like that. So that's where we're headed. And this is the last slide. All these picture missions, I think, are going to be fill a gap, certainly, in where we are now, until we can do a full, huge, flagship-style mission. And we can keep testing and reflying and building all of these, developing all these technologies for doing one day imaging an Earth-like planet around a Sun-like star. So that's all. Thank you. If you look up here, there's a...
Are there separate things?
What's that?
That's on a loop, right?
That's a loop.
That's not like...
There's a little... No, yeah, it's a loop. There's a little shooting star up there.
Thank you so much, Chris. Are there questions from the audience? Let's start with Greg.
Chris, thanks a lot for the nice talk.
I'm just wondering, so I want to understand how much do we gain by launching this on the balloon. So if you were just to use this telescope on the ground on a good night with clear sky,
yeah,
what would be roughly the range you could suppress the star?
We would have to retune the AO system to work in a completely different way. So we would have to run that big DM, we'd have to run that really fast to be able to keep up. So, if we just ran it as is, we would get typical 1 arcsecond seeing on the sky, 1 arcsecond blurriness, right? So it's 1,000 times worse than what we need. So that's why we need to go up into space. So if we ran the AO system really fast and kept up, we would need different wavefront sensors and everything. So this is not designed for that. But if we had a more of a ground-based, so that's what they do on ground-based telescopes. They have really fast AO systems that can keep up with the atmosphere. And they can do reasonably well, but they can only get to, we talk in contrast units, so 10 to the minus 6, a million to 1. We need to get orders of magnitude below that to eventually see Earth.
Right, and this is just from aberrations in the atmosphere.
Yeah, yeah.
Actually, can you pass it to John?
So I guess I have the opposite question.
Yeah.
How many of these problems solve themselves if you're just in space and not dealing with a balloon? How much better would this instrument work?
Right. The stability would be better. The sort of the pointing stability and all that. So that part of it would be easier. I think the thermal deformations would be easier depending on what orbit you're in. We've talked a lot about doing this in low Earth orbit, where you're having constant in and out of sunlight cycling of the telescope. That can be difficult to deal with. We see it even, we slew the telescope to point with the sun to our back. The thermal environment changes completely. So if we're in space, it's going to be probably even more dramatic. But I think, I don't know, no one's ever done this in space, so it's hard to know how well modern telescope pointing systems work. I think if we had like a Hubble-class spacecraft bus, then we'd be okay. But all the dark hole stuff, digging the dark hole, using the DM for that, that's all the same. That has to be done the same way in space. Yeah.
Other questions?
I can just yell it. Is there any sort of active cooling on the payload to maintain thermal stability, or is everything operating at ambient?
There's a lot of heaters. So yeah, we're fighting, for the most part, we're fighting getting too cold. During the day, if the sun hits the wrong part of the payload, it can get too hot because it's really hard to cool off because you're basically just radiatively cooling. So that's why we paint the whole thing white and then we wrap the whole thing in mylar to shield it from the sun. So it's relatively shielded. But we do a lot of really precise temperature controlling on certain parts. We fly a lot of off-the-shelf components, right? So we don't have a satellite budget, so we can't buy space-qualified computers and we can't buy space-qualified certain devices. So we fly off-the-shelf ones. If they need to be ruggedized, we do that. If they need to have heaters on them, we do that. And then we do a lot for just optical stability in the coronagraph itself. We have a lot of control loops running on heaters to keep things as stable as possible. But you can imagine trying to keep, picometer level stability with this deformable mirror. If the whole thing is changing temperature, it gets to be really difficult. So we haven't got to that level yet. We're still in the nanometer regime. But as we get further and further, I'm sure we're going to discover all sorts of more issues we have to solve.
Other questions? If not, can I ask you a very simple-minded question, which is, so you talked about having to get the centering absolutely right.
Yeah.
For the nearby stars, are you going to end up with a problem with the fact that the stars aren't point sources?
Yeah. Yeah, so resolving the stars is an issue. That's why we don't look at Betelgeuse or some really, really big giant star. We try to keep with dwarf stars. You'll get leakage from resolving stars. Certain coronagraphs are more tolerant of that than others. There are nulling coronagraphs that have extremely sharp nulls where a star that's 5 milliarcseconds across will completely swamp the image. This vortex technology is pretty robust it's analogous to, the stellar size is analogous to Poynting error because it's just smearing the star over. So we can tolerate up to an 8 milliarcsecond star.
Okay.
So that's nearby, yeah.
Nearby, but
right, yeah, so nearby, yeah. So as you go to further stars, that gets easier, but then you need a bigger telescope to get in, so the problem doesn't really go away.
Is that better with a star-shaped coronagraph?
I don't know. Probably not.
All right. Oh, Sarah.
Is there a role for machine learning algorithms?
Yes. You want to help us?
No.
Okay. I think all of those wavefront sensors need machine learning applied to them because they're all nonlinear systems. And then I think a lot of the data processing also would really benefit from machine learning because, and people are definitely working on that. We have a tendency to, all of these problems, we just throw linear algebra at them and break things into principal components. But in reality, we do need machine learning to do complex pattern recognition and things like that. So definitely. We have trouble getting them to run really fast. That's the trick. We need to kilohertz machine learning algorithms.
Yeah, I'm just wondering about the flight duration in a balloon.
Yeah.
Do you have any hopes for a long-term
Yeah.
flight?
Yeah, so from New Mexico, you can only do a single night. And it's tough. You have to launch in the morning because of the wind, how the winds work. And we want to observe at night because even though we're that high up, the sky still has some background. So we got to fly. So it's 24 hours. And then by 24 hours, we didn't even make it 24 hours. You've drifted over. You could be in Mexico or you could be over the ocean. So that really limits. But the site we're looking to is New Zealand. There's this facility there that does these ultra long duration balloons where you can fly at a fixed latitude around the planet through many day-night cycles. And we need day-night because we need to charge solar panels during the day. Charge up our batteries during the day and then run at night. So that's the idea. That's what we're trying to get to. And then you could do 100 days. You could fly around. And that would be amazing. So that's where we're trying to get to. We're trying to convince NASA to give us money to do that. I think they want to see us prove that it works. That's hopefully at this level. So we've just done this. So this hopefully will give us some more leverage to get to that point. Yeah.
Excellent. Let's thank Christopher again.
Thank you, guys.